questions on the half-life of an M&M. So you should have already done the experiment and done the actual data collection of this experiment. If you need to, I will flash real quickly the steps and procedures on the screen for you to be able to go over. Here's the goals of the lab. So what the lab asked you to do, you want to define the terms half-life and radioactive decay. We want to model the rate of radioactive decay. We want to create a line graph from data collected, which I'll show you in a second, an example of one. We want to compare data from one class to the next, and we want to understand how radioactive decay is used to date archaeological artifacts. So here's what we needed: a bag of elements, which could have been M&Ms, pennies, or puzzle pieces, and you just needed 10 of them. You need, you don't necessarily need paper, and you don't need graph paper. You need that sheet off of Canvas, the data collection sheet, Ziploc bag, or something to shake up the M&Ms in. We used a cup in class. If you're getting desperate, you could even use something like a sock. You don't really need to use a pen, marker, or ruler or pencil because everything is online. Here was the procedures. What you did, you put 10 of the elements into the bag, shook it up, and then dumped them out. Any of the ones that still had the M on face up were considered to be radioactive. And then you put those back in the cup and recorded those under trial. Then you shook up and you repeated again and again until you got to trial number 7, or all of your M&Ms were no longer radioactive. So here is where we begin our post-lab discussion. The very first question should be easy for you. It asks you to define the term half-life. And we define that in the lecture as the time it takes for half of the atom to decay to a stable state. So after they have undergone this, half of the atom will be stable and the other half will still be radioactive, meaning that it's going to further break down. What does it mean to say when an atom has decayed? Now, that's something we didn't exactly talk about, but in fission, which is the process that's happening, the atom has fissioned into 2 or 3 smaller parts, generally giving off gamma energy, and is now in a stable state. So to decay means that we once had a big, like if you think uranium, we had a big atom and it was unstable, and because it was unstable, it wanted to split. And it did. And when it splits, those 2 things that it split into are no longer radioactive. They're generally stable. So when they were together, they were unstable. They wanted to split. It's like if you and your sibling were in the same room together for too long, you eventually want to split. And then when you do, you're stable. Okay? So I hope that makes sense. So it means that the element is no longer radioactive. Do the number of atoms you start with affect the outcome? What do you think? So if you had done this experiment and did like 100 M&Ms instead of 10, you should have got the same results. So no matter the atoms that you start with, you should still see the same kind of general trend result that you got when you collected your data today. So it shouldn't matter. However, it does matter. One of your other questions asks, why do the totals for the 10 groups better show what happened during half-life rather than any one group's results? In science, we talked about in order to be statistically significant or for your experiment to be taken seriously, you have to have a lot of evidence, a lot of data points supporting your results. So just doing it once yourself wasn't enough results to be statistically significant, so we needed to repeat it. And in our case, we had 10 groups doing the same experiment at the same time, giving us a larger body of data to analyze. If you do an experiment only once, it's likely that you might have gotten the result due to random chance. That's why scientists often repeat experiments again and again to be sure that the results that they got were supportive of their hypothesis. Going back, actually we can finish answering these questions and then we'll look at the graphs. Did each group get the same results? If you were in class with us, you noticed that not all of the groups got the same results. By the end, generally, we all decayed, so we actually didn't have any groups that had candies remaining after 7 trials. All of them were 0. But did each group get the same results? Yes or no? We did not see that. So we got similar results, like we'd lose a lot of M&Ms on the first round, and then maybe not so many M&Ms on the second round, but we did not get the exact same results. So that shows a little bit of variation within our experiments, and that's again why we do experiments again and again, to be sure that our results are statistically significant, meaning that the data that we discovered didn't happen by random chance. Okay, so that was those 3 questions, and that should be the majority of your post-lab questions. Might be one more. There's 2 more. So what happens to the total number of candies after each trial? You should have seen that about half of what you started with for each trial decays. So if you were to spill your M&Ms, about 5 of them would turn upside down, while the other 5 would be right side up. So we saw that about half decayed. And then how do scientists use radioactive decay to date fossils and artifacts? Let's talk about that for a second. So by looking at the ratio of carbon-12, which is the stable isotope of carbon-14, you can calculate back to the amount of original carbon-14 using the half-life of carbon-14 to equal 5,000. It's 5,730. So that means, by looking at the ratio of carbon, so that means that if I know the ratio of stable versus unstable, I can calculate how much carbon-14 was there to begin with. And I can also tell from that number how old the rock was as well, depending on how many half-lives the carbon has gone through. So this is how we get that actual data. So I know that if I have exactly half of the amount, so say I've got 5 grams of carbon, or say I've got 5 grams of carbon and 5 grams of carbon-12 in my experiment. So let's figure out how to draw that for you, so that you understand what I'm saying. So if I have 5 grams of carbon for 12 and 5 grams of carbon 14, my ratio I can assume that 1 half-life has happened since the rock's formation. That means that the rock is about 5,730 years old. Good. Now it gets a little bit tricky once we pass 1 half-life, because then we have to figure out things exponentially. But that's a good general rule of thumb right there. Okay. All right, and back to our graphs real quick. Maybe. We'll give it a second to warm up. So, but we saw, we'll just look at it right here. It's not going to cooperate. Here, if we had graphed this, this is what we would see. So after 0, we've got all of the amount of carbon-14, or all of the elements, the M&Ms are radioactive. And then what we should have seen after trial 1 is that about half of the M&Ms became unradioactive, so about 5. And then as we went to trial 2, about half more of those half should have become unradioactive, so like 2.5, but you can't do 2.5, so maybe 3. And so now you only have 2 M&Ms left. About half of those in trial 3, so 1, would have become unradioactive, bringing us just down to 1, and then to eventually 0. So you can see how it doesn't, well, it does take long, because half-lives take a long time, but we can quantify, because of the half-life and how it works, exactly how much time has passed in between each if we know the original start. So we call, and we'll talk more about this in our other lecture, but we call the material that we started with, so that radioactive material, to be the parent material. We call that parent material. And then our daughter material is that stable isotope that we get after the atoms have fused. We call that the daughter. If you can see in my graph here, when we first start, we've got 100% of that parent material. But then as time moves on, we get a 50-50 ratio in our first half-life session. And then as time continues to pass, we get a 75-25% ratio, because this half of the unstable isotope split, and then that joined the other half, and then we split this further into half, which is 12.5, and we split this into half, which is 6.2, and it continues to go down until you have no more of the parent material left. And because we know, like this is cobalt, because we know how many years passes, or how many years it takes for cobalt to break down, we know that if we find like 75% here of the daughter material and 25% of the parent material, we can infer that 10.6 years have passed since the formation of this rock. Pretty cool, right? All right, so we're going to further continue investigating this in your video lecture about absolute dating. A lot of it is going to be review from your lab. It should be a pretty short lecture. Okay, have a great day, guys.